Okay, so in the previous video we set up the problem. We had our circuit that we could not where the resistors could not be combined in series or in parallel. So the first step was to assign currents in all the branches and uh, and their directions, which were totally arbitrary. And now we have to set up equations and solve. Now, obviously, we need as many equations as there are unknowns. So how many unknowns did we have? We had three unknown currents, I1, I2, I3. So we're going to need three equations. The fourth step is now we're ready to apply the voltage loop rule. Uh, by that, that's the rule that says that if you go along any closed loop, the sum of the voltages, which is the same as which are difference of potential, the sum of the voltages along a closed loop must be equal to zero. So how do we actually apply that? First, you take your circuit, you pick any point you want, anywhere you want, you start from there, and then you follow a closed loop throughout your circuit. And as you go around the loop, you add all the voltages. So the rule says that if you add all the voltages as you go around your closed loop, you get the sum must be equal to zero. But you must be careful with the sign. The signs are crucial here. You must assign the correct sign. It can be a positive voltage or a negative voltage. If the potential goes up, your voltage is positive because delta V is positive. If the potential goes down, the voltage is negative. We're going to see an example in a minute how that works. Okay, but that will give us an equation. The sum of the voltage along a closed loop equal to zero. Now, unless you have a very simple circuit where you have only one loop, usually you have several loops. So when you apply that, you will have gone through one loop, but you won't have covered all the branches in the circuit. So what you have to do is that you have to repeat this step for other closed loops until you've went through all the branches of the circuit at least once. Okay, so you might have to do this, set up these, apply this rule to several loops. We'll see an example in a minute. Okay, well, let's go back to what we had last time. Remember where we stopped? We had assigned the three currents and their directions, and remember the choice of the directions was totally arbitrary. So we made those choices shown here. I1 that way, up here, I2 up here, and I3 to the right. Now we're ready to apply the voltage rule. I'm going to pick some point in the circuit. It can be anything. Let's pick that one here. Let's start here. And what I'll do is that we'll go around a closed loop. Now, the direction in which I go along my loop is totally up to us. Okay, it's up to us. You can go clockwise in the loop, or you can go counterclockwise. It's arbitrary. You don't have to pay attention to the currents to choose your direction in which you go along your loop. So I'm going to choose to go clockwise. So I start from this point here. I go up, not because the current is going up here. I'm really not paying attention to the current. So I just chose to go clockwise. So I go up, I keep going, and I keep going this way. Now at this point I have a choice. I could go on the outside and close my loop this way by coming back here, or I can go down here. I'm going to choose to go down here, but this is totally up to me, and I'll come back and close my loop. So I have in red here my loop, and I chose to go clockwise along this loop. I could have gone counterclockwise, and the equation would still be correct. Again, I want to emphasize that the direction in which I go in my loop here has nothing to do with the directions of the current. Because you see, the current here, I1, is going up, but by the time I go in this branch, when I'm going along my red loop, I'm going opposite to I2. So I just pick a closed loop and I choose one direction and I just apply the rule. Okay, I don't have to pay attention to the currents. So now we're going to set up the equation. So I chose my loop, I chose to go clockwise in my loop. I'm starting at this point. Now as I go along my loop, I'm going to add all the voltages of all the elements. So first I'm going through the first battery. Now the polarities are important here. They will tell us the sign of the voltages. So here, as I go along my loop this way up, I go from a point of higher potential to a point of lower potential. Okay, the plus and minus signs here are what we call the polarities of the battery. But what they tell us really, they tell us that this point here on this side is at a higher potential than the point here. So as I go this way, because I chose to go clockwise in my red loop, as I go this way, the potential goes down. I go from high potential plus to low potential. So as I go that way, the potential goes down, which means the voltage will be negative, and it will have a value of 9 volts. So as I go this way, I get minus 9 volts. When I set up the equation, I won't bother writing all the sig figs, like 9.00, I'll just write as 9, and we don't have to write the units. It will just make the equation simpler. So instead of writing minus 9.00 volts, I'll just write minus 9. So I have minus 9 here. I keep going. Now I go from higher potential to low potential. Remember those polarities that we assigned in the previous steps? Now they're very, very important. So I go from high potential to low potential, so the voltage will be negative. But what's the voltage here? I don't have a number here because it's a resistor. But I know that the voltage across a resistor is given by Ohm's law. Is the resistance, which is 5 ohms, multiplied by the current in that resistor. What is the current in that resistor? We don't have a value, but we called it I1. So the voltage across here in absolute value is just 5 ohms times I1. So 5 I1. That's the voltage. But the sign, because of the polarity here, I went from there to there. The voltage is negative because the potential decreased. So as I go that way, I get a voltage of minus 5 I1 here. Okay, so this term here is the voltage I went through as I went from this side to this side. Okay, I keep going like this here. This time now, as I go through this resistor, the potential increases. I go from the lower potential to higher potential. So as I go down, the potential goes up, so the voltage will be positive. What is the voltage equal to? It's positive, but what's the value? Again, I use Ohm's law. I know R2 is 6 ohms, and I know the current flowing here now is I2, right? This is I2 in this branch. So as I go that way, the voltage will be plus 6 ohms times I2. So I get this term here, plus 6 I2. Again, I didn't write the 0.00 and I didn't write the units of the resistance, but that's the voltage as I go this way. And then I keep going in my loop. Now I go to this battery. I go from a lower potential to a higher potential. So the voltage will be positive as I go this way. The voltage is positive because the potential increases by how much? It increases by 15 volts. So I have a plus 15 volts as I go this way. And I keep going, but now I don't, and I come back to my initial point without having crossed any other element. So I'm done. I have now that the sum of the delta V in my closed loop is given by all those terms here, and that must be equal to 0 because I'm back to my initial point. This is it. This is an equation for that contains I1 and I2. Notice it does not contain my other unknown I3, but that's okay. As long as I have an equation, it will be useful at some point. So that's my equation I got from the equation I got from this closed loop here. Now, I should simplify as much as possible before going further. So I can, of course, combine the minus 9 and the plus 15 to get plus 6. And then after that, if I could simplify even further by dividing and so on, I would. But then I cannot do much here. Whoops. So, sorry, I get this. Okay, I combined my minus 9 and my plus 15 from my two batteries into plus 6. So I get 6 minus 5 I1 plus 6 I2 equal to 0. This is my first equation. Okay, so we've applied the loop rule to this loop here. Now, as I told you, we keep going until we've covered all the branches. So this branch here has not been covered yet. So I'm going to repeat again. I take an arbitrary point. Let's say I take this point. and I'll go along a closed loop. Now, I'm going to choose to go again clockwise, so I'm going to go this way, and I'll go. So let me use a different color for this other loop. So let's say we go this way here. So I go down here, this way here, and now I have again the choice. I'm going to choose to go this way, and then close my loop this way. Okay, so this is the loop I'm going to follow, and I'm going to add all the voltages. So what do we get if we do that? Okay, so now that's it. That's the new equation we get. I'll show you again where it comes from. So we're going here. I'm going here. I'm going here. Now, as I go here, the voltage is positive because the potential increases. So I go from a lower potential to higher potential. It goes up by what? It goes up by 7 ohms times I3. So that's it. That's my first term here. So I get plus 7 I3. I go here, the potential decreases by 15 volts. So I get minus 15 volts. Okay, I'm here. Then I go through this resistor, the potential decreases, so the voltage is negative, and it's equal to minus 6 ohms times I2, because I2 is the current going here. So delta V here is 6 times I2, and it's negative. So I get this term here, minus 6 I2, and I keep going like this here. Then the potential increases by 12 volts. So I get the plus 12 here, and I'm back to where I started from. So the sum is equal to 0. Again, I simplify. Minus 15 plus 12 gives minus 3, and I get this simplified equation that I call equation 2. Okay, now at this stage, we have covered all the branches. No, the first loop was here, and our second loop is here. So now we covered all the branches of the circuit. So that's our 3 equations we get from the voltage rule. Okay, that's it. We have used the voltage rule as much as we can. As soon as you have covered all the branches, you stop using the voltage rule. So we need a third equation. How do we get the third equation? That's the 5th step. Now we pick a junction and we apply the junction rule, which, remember, says that at any junction, the sum of the currents coming in is equal to the sum of the currents coming out. Okay, so let's apply this. By the way, here I keep applying that to as many junctions as I need to complete the number of equations that I need. Remember, we have 3 unknowns. We got 2 equations from the voltage rule. Now we just need 1 more equation. So I'm just going to apply that in our case to just 1 junction. So what do? I pick a junction. I could anything I want. I can pick that one or that one, doesn't matter. So let me pick this one here. So the sum of the currents that come in is equal to what? It's equal to 0. There's no current coming in. That 0 must be equal to the sum of the currents coming out. They're all coming out. So that gives me this equation. The sum of the currents coming in equals 0 is equal to the sum of the currents coming out, which is I1 plus I2 plus I3. This is my third equation. And that's it. I have 3 equations, 3 unknowns now. Let's summarize. Okay, so now we're done. All we have to do is to solve. This is my first equation from the first loop, from the second loop, from the third loop. You have 3 equations, 3 unknowns, then it's just algebra. You solve, and you'll find that the solutions are given by this, I1 0.5608 amps, which I can now round off to 3 sig figs, and I'll convert to milliamps. It's just a nicer number, but I could leave it in amps. So that's I1. I2 comes out to be minus 533 milliamp, comes out negative. I3 is minus 28.0 milliamp. Okay, now we said that currents are never negative. So in this approach, using Kirchhoff laws, the sign here tells us something. What does it tell us? When you get a negative current, what it tells you is simply that the direction you had used at the very beginning was just the wrong direction. Okay, so now we're going to use that to figure out the correct direction. Now here, this is exactly what we had chosen at the beginning, right? We had chosen I1 up, I2 up, I3 to the right here. The fact that I1 is positive tells us that this direction here, the choice we had made, was correct. So that's the correct direction for I1. The fact that I2 and I3 are negative tells us that those directions here that we had picked were just the wrong directions. So now, as the very last step, I redraw the circuit with the correct directions. So I'm going to flip I2 and I3 because they're both negative. So this is the final solution. This is the circuit drawn with the currents in the correct directions, and now I gave their values. They're all positive now because I drew them with the correct directions. And that's it. We've solved the entire circuit. Okay, and so this is how we apply Kirchhoff laws to solving circuits. Okay, we'll practice that in class soon. Thank you.